Mechanical engineering applies to the principles of engineering, physics, and materials science for research, design, manufacture, operation, and maintenance of mechanical systems. Chassis of all kinds are generally an assembly of multiple spring elements, which whilst in motion undergo constant vibration and distortion. A performance damper is essentially a shock absorber designed to curb micro-distortion by intentionally increasing the chassis' viscosity. How are performance dampers used in everyday applications? Modern-day motor vehicle chassis are comprised of many elements which undergo continuous vibrations and distortions whilst in motion. Dampers are used in all forms of motor vehicles ranging from cars to snowmobiles.
Differential equations have a wide variety of applications in various strands of mechanical engineering. Modeling variations of a physical quantity such as temperature, pressure, displacement, velocity, stress, strain, or concentration of a pollutant with the change of time t or location such as the coordinates x, y, z or both would require differential equations. It's one of an engineer's main roles to be able to compute physical problems with the variable changes using mathematical equations. This is what has given rise to the need for the differential equation. A first-order differential equation is said to be linear if it has the form as shown. These are generally solved using integrated factors, which we will demonstrate today. A small engineering company produces hydraulic dampers for specialized applications. One of the test rigs used by the company to check the quality and consistency of the operational characteristics of its output is illustrated below. A carriage carrying a mass is projected along a track with very low friction at a controlled speed. At the end of the track, the carriage impacts into a buffer which is connected to the damper under test. Prior to impact, the carriage passes photocells used to capture the speed. The time/displacement history of the damper is compressed and recorded digitally. In order to interpret the test results, the company needs to know how a damper should, in theory, behave under such a test. We can use the first-order dE to compute the velocity and displacement curves and compare these against theoretical-based models. The compression of the damper can be described by the equation m dV on dt equals minus kV minus b, with the condition of v equals u when x equals 0. First, we rearrange our equation getting kV onto the left-hand side. We then divide out by m. Standard form for a dE is shown above. Our integrating factor is e to the integral of p dx, which in our case, k over m is lambda, so we have e to the integral of lambda dt, which equates to lambda t. First we multiply out our integrating factor, then we refine our dE into its final form. We then integrate.
After we integrate, we get this equation at the top. We get v e lambda t is equal to negative b over m lambda times e lambda t plus c. We then refine this to give us our final solution of v. This is our given initial condition for the equation. We will now use this to substitute into our derived equations. Substituting in our initial condition into our velocity equation now gives us our equation which will determine our velocity time curve. If we integrate this equation one more time, we will derive our displacement time curve equation.
We can now see that using the parameters as described above, we have derived our velocity time curve and displacement time curve, as shown. We can see how differential equations are used as an analytical tool. Equations such as these are invaluable resources as it allows engineers to easily specify appropriate parameters to meet operational specifications and requirements.